All right, so the climate change that we're experiencing is ultimately the result of shift in an equilibrium system with this cascading effect of creating shifts in many, many equilibrium systems. All right, I think you guys got a pretty good feel now for the warming of the atmosphere. All right, but other things like how does burning fossil fuels in a factory cause coral bleaching? All right, we're going to take a look at those connections here so you can start to see that we really have not just one equilibrium system, we have many equilibrium systems. And we're just going to look at a small component of the equilibrium systems, very small component of the equilibrium systems going on this Earth. So we're going to focus first on ocean acidification. All right, the warming atmosphere, of course, is causing a rise in ocean temperatures. Okay, and some of you researched that in December. Some of you even saw how the rising local temperatures, all right, in specific areas have caused fish and other ocean life to migrate, trying to find colder waters. And we've seen that those things that like the colder waters are moving further north. But CO2 also reacts with water. It doesn't just help trap heat in the atmosphere. Oceans actually absorb a lot of the CO2 from the atmosphere. So a lot of what we add to the atmosphere doesn't stay there. A lot of it actually ends up in the oceans too. So when we add CO2 to the atmosphere, we're adding some to the atmosphere and some to the oceans because the CO2 will react with water. And that's actually a really simple lab that you can do. If you get a hold of any sort of acid-base indicator, then you can just take a straw and blow into some water that has your acid-base indicator in it. Right? There's cabbage juice indicators. You can actually make it home if you're bored this summer. Right? You can watch it change colors to indicate it becoming more acidic just by blowing into it. Okay, it's pretty cool. So here's our equilibrium system here. CO2 plus H2O makes carbonic acid. So obviously if we add more CO2, we're going to shift it in that forward direction. Okay, which is what I just said. Adding CO2 to the atmosphere shifts this into the forward direction. And carbonic acid is known as a weak acid. Weak acid, which most acids are, means that most of the molecules stay together and don't really affect the pH. That doesn't mean they can't do all sorts of crazy things, all right? And weak acids can cause lots of damage, all right? It's not just strong acids that can cause damage. But a weak acid means a lot of the molecules stay together and don't affect the pH. This is the ion here that affects the pH. And this is an oversimplification. It's not quite exactly that. It's technically stuck to a water molecule. We won't go there right now. So when we form that carbonic acid by adding CO2 to the atmosphere, all right, we shift this forward up here. So now that we've added more carbonic acid, this equilibrium is also going to shift forward. So we're going to make more of that ion that makes the pH drop. The ocean is actually slightly basic. It's not neutral. Basic means it has a pH higher than 7. Basic also means that it contains more hydroxide ions than the H+ ions, and that's what makes the pH higher than 7. Neutral does not actually mean no hydrogen and no hydroxide. Neutral means equal amounts of hydrogen and hydroxide. They have equal concentrations. All right, so we have this other equilibrium system here where now we've made more H+, it's going to react with some of the hydroxide that's in the ocean, right? And since we've added H+, it's going to push this equilibrium forward, basically meaning now there's going to be less hydroxide, more hydrogen, and that's going to cause the pH to drop. Okay, we can see that on here too. Okay, concentration of hydrogen, sorry. All right, the pH scale is logarithmic. You may not have really learned about logarithmic scales, all right? But what that means is a small change in pH is actually corresponding to a really big change in concentration. If your pH drops by 1, right, that's not a small change in concentration. That means it's 10 times higher in the concentration of the H+. So we've got some data over here showing the pH of the ocean, all right, pre-industrial, recent past, and present levels. And we can see it doesn't look like the pH has really dropped that much, but when you consider pH being a logarithmic scale, that means the concentration of hydrogen has increased by almost 30%, which is a much bigger change than it sounds like when we just see this tiny little pH drop. It's really a big change. And all the ocean life is more adapted to this slightly more basic pH around these ranges. So this is going to have further implications. All right, it's just like you can't put, saltwater fish in fresh water. They're not adapted for that. Well, you start messing with the pH of the ocean, and it's going to take longer for everything to adapt to those changing environments. And we're not giving the time for those adaptations to happen. All right, as you learn about in bio, adaptations take a very long time. So we're going to pull this together and kind of add a piece. Okay, so we have more CO2 in the air. All right, that shifts the equilibrium to produce more carbonic acid, which produces more H+. We also have this equilibrium here, so we're adding a piece. We have carbonate ions in the ocean, all right, that can be in equilibrium with water to make hydroxide and bicarbonate. Okay, so when we add that H+, all right, if we shift this forward, well, as that reacts with the hydroxide, right, we've seen that reacting with a component of the system, removes it from the system. So now we're talking about removing some hydroxide from the system. Well, that's going to pull this equilibrium forward, and that's going to cause there to be less carbonate available in the ocean. I think, okay, so what? All right, so there's less carbonate involved in the ocean. All right, before I get to that, I'll just address a note down here for those of you reading what's on the slide. It talks about buffered water resisting changes in pH. The ocean is actually doing a pretty good job of trying to resist the change in pH. All right, and even though it is doing a good job of resisting that change, the pH has still dropped by 0.11. Okay, so buffered solutions, they help. They try to prevent that change, but they can't fully prevent it, and things are still going to change even in a buffered system. Okay. All right, so back to carbon. There's a lot of shelled organisms in the ocean that construct their shells using that carbonate ion. So if there's less carbonate available, shells are going to be weaker and organisms aren't going to live as long. And some of you found that out when you're researching December, right? But again, the links of, well, we put CO2 in the atmosphere, and so now shelled organisms have weaker shells, right? You guys didn't know enough science about these equilibrium systems to put all of those pieces together and understand why that would be. Coral reefs also use carbonate, and so they can't grow as well or as strong with less of those essential building blocks to work with. Okay. Some of you might be thinking back saying like, wait, but what about that calcium carbonate on that last slide that was like in the minerals and everything that was way at the bottom of that picture, if you saw that. It takes a long time to get the calcium carbonate out of those. So if you're shifting these equilibriums too quickly, then that's not going to keep up. Okay, so it can't simply just replenish the carbonate as quickly as it is being used up. So here's a couple of pictures of coral reefs, all right, just like real photographs of how things have changed over time. All right, if you start depriving the ocean of the carbonate and you're increasing the acidity as well, all right, you can see how these once vibrant coral reefs, all right, this one, all right, are getting what's called bleached. They're turning white. They're basically dying. Right? They're not the vibrant places that they once were. And of course, all the fish that depend on a healthy coral reef, well, they're going to suffer too. They don't have those homes to live in anymore either. And we've got this one as well. Just have one more picture of that. So a few weeks ago, you probably were like, okay, collision theory. All right, okay, great. There's 5 factors that affect collision theory. And one of them was concentration. And then I had you learn about the driving forces, all right, so that you could understand, how its system would be able to set up an equilibrium and what an equilibrium means and what an equilibrium looks like. You do that through your kitchen labs and videos. All right, we saw how equilibrium is affected by disturbances. We saw what a shift looks like in equilibrium. And the reason we went through all of this is because if you don't understand any of that, then how can you help find ways to solve the problem or at least lessen your own impact? Because if you're not informed about the problem, you can't take any action to try to help. So I hope that you see what those last few weeks were building to here. I hope you found it worthwhile. All right. And this is what I have to leave you guys with right now. Okay. Hopefully you will attend our final conference on Friday. All right. I hope to see you all there. All right. And either way, I hope you guys have a great summer. I know this is a crazy, crazy situation that we're all living in. All right. So on Friday, be prepared to help maybe share ideas about what you've been doing, try to stave off the boredom. All right. As there may be more days of that to come. All right. Let's all help one another out. Okay.